Thank you for joining us. We have Josh Gilbert with us today. Josh is a doctoral candidate at the Harvard Graduate School of Education, where he's advised by Dr. James Kim and Dr. Luke Meritrix. His research interests include the intersection of psychometric and causal inference methods in education and the social sciences. His work has been published in outlets such as the Journal of Policy Analysis and Management, Behavior Research Methods, and the Journal of Educational and Behavioral Statistics. So please join me in welcoming Josh Gilbert.
Thanks so much, Clint and everyone. It's great to be here today. Let me share my screen here. Are the slides visible? Get a thumbs up. Awesome. Okay. So today I'm going to be talking about a paper of mine with some colleagues, Zach Himmelsbach, Jim Soland, Mridul Joshi, and Ben Domingue, called Estimating Heterogeneous Treatment Effects with Item-Level Outcome Data. As Clint says, I'm happy to take clarifying questions throughout if you put them in the chat, which I'll ask Clint to monitor for me. But we'll save substantive questions at the end. We'll have plenty of time for discussion, and the slides do have numbers in case we want to go back to anything in particular. So just a little bit of a preamble before I dive in. So this manuscript is accepted at the Journal of Policy Analysis and Management, JPAM, in their methodology section, and I do have a preprint out on archive if you'd like to read the full paper. There's a QR code here. I also have it at the end and can share the link. So here's what I'm going to talk about today. I'm going to start with some motivation. As Clint mentioned, one of my big driving research interests is the intersection of causal inference and psychometric methods. So I'll motivate today's talk with a little bit about this idea of building bridges between psychometrics and causal inference. Then I will show some visualizations to help us get some intuition on what I mean when I say item-level heterogeneous treatment effects, which I'll be talking about throughout this presentation. Then I'll represent this model mathematically to really get specific on what do I mean by an item-level heterogeneous treatment effect, how can we model it, how can we interpret it. And then the real heart of the paper it's almost a meta-analysis. It's a survey of 75 empirical data sets that I have gathered and analyzed using this method from randomized control trials with item-level outcome data to see what we can learn from these sort of models in practice. And then I'll summarize and conclude. So as I said, I'd like to get started by contextualizing this project as part of a broader goal of building bridges between psychometrics and causal inference. And just for a moment, I'd like us all to consider a randomized control trial, or an RCT, with a psychometric outcome measure. And by psychometric outcome, I mean something not like income or, whether you lived or died or, how tall you are, but something more like mathematics proficiency, self-efficacy, growth mindset, something we can't observe directly, but instead measure through some sort of psychometric instrument. And my colleague, Ben Domingue, who's also co-author in this paper, likes to say, and this is a paraphrase, spending a lot of time and money implementing a rigorous RCT and then ignoring measurement is like being very careful when baking a cake, using all the best ingredients and techniques, then throwing in salt instead of sugar at the end. And I really love that quote, one, because it's very evocative, but two, I think there's a lot of truth to it. We do spend a lot of time and money implementing rigorous RCTs, and we should. They're one of the best tools we have in the social sciences for determining what works, governments, universities, nonprofits. It's sort of our gold standard toolkit. But I'm going to argue we're leaving some information on the table when we don't consider measurement considerations. So the guiding question for today is a really simple one. I come from education, which is how I'll sort of be framing a lot of this, but everything I'm going to say also applies to health sciences and other social sciences. But in an RCT in education, we almost always collect what I call item level data. For example, if I give you a math test with 20 items on it, like your responses to those 20 items exist somewhere, but most often we just use your total math test score in our analyses. So the guiding question here is, how can we leverage this item level data more effectively in randomized control trial contexts? And just to illustrate why this might matter, there's an implicit assumption in most models for, say, a causal effect of an educational intervention, which is that first we would give people a test, we would then score that test, give everyone a score, a single number score, and then estimate a treatment effect on that test score. And the implicit assumption here is that all outcome items are equally affected by the treatment. And the first thing I want to point out is that this simply need not be true, right? We could have a math test with 20 items on it, and some of those items could be really improved by treatment, where other items might not be affected by the treatment. And I'll argue today that item-specific sensitivity to treatment could be telling us really important information about how interventions affect outcomes. And while I think it will surprise no one here to learn that researchers have paid a lot of attention to heterogeneous treatment effects, or HTE, at the person level. For example, do treatment effects vary by age, by gender, by pretest scores, by site? Again, I'm arguing why not extend this exact same logic to the item side of the equation? Do treatment effects vary by, for example, a multiple choice item versus an open response item, easy items versus difficult items, one-digit addition versus two-digit addition, and so forth? So I'll introduce a model I call item level heterogeneous treatment effects, ILHTE, that allows for this. In a very straightforward framework, we can get a unique treatment effect for every item of the outcome measure. And then, as I said, I apply this model to 75 data sets from 48 randomized controlled trials to illustrate the affordances of the method. And this gives us about 6 million total item responses that we're working with. I'm going to argue that we get 5 insights from this model. So I'll state them here. And then after I introduce the model, I will illustrate them with the empirical data. So the first thing we can get from this modeling approach is the estimates of the item-specific effects and their distribution. Number 2, we get what I will argue to be more realistic standard errors for our treatment effects that account for the selection of items onto a test. 3, we can calculate prediction intervals that help us understand how generalizable our treatment impacts might be to items that were not tested on a given test. Number 4, turns out that when we have item-specific treatment heterogeneity, this can create some weird biases in treatment by covariate interaction effects, but we can correct for this by using the model I'll present today. And then last, but certainly not least, is that we can get unbiased estimates of standardized effect sizes, which are really important in policy and in meta-analysis. So I'd like to begin with some visualizations to help us understand this idea of heterogeneous treatment effects generally, and also then how this applies to the item level. So I'm going to borrow a visualization from Andrew Gelman, or rather adapt one that he calls the causal quartet, where he asks us to imagine 4 different worlds represented by the 4 panels of this graph. And on the y-axis is some causal effect of interest. And across all 4 of these worlds, the average causal effect is 0.1, and that's represented by that pink dashed line. And what Gelman asks us to notice is that the same average can be generated by many different underlying combinations of raw data. So for example, if I'm in the top left row, or it's the top left panel, excuse me, that treatment effect is the same for everyone. And what I'm showing on the x-axis could be any covariate, these could even be individuals, versus say the bottom right figure where we have only 2 of these subgroups, groups 4 and 8, showing large treatment effects, and the remainder showing null treatment effects. And immediately we can see why we might care about this. For example, if I'm in, say, health or public policy, if I can identify the groups or the subsets or the covariates upon which treatment efficacy is likely to depend, I can target my interventions towards where they would be most effective. And of course, it might not be so clear. We might just have some variance around that average, and that could be low, or it could be really erratic, and we might have some groups that are hurt by treatment, some groups that are helped by treatment. And understanding those patterns is really critical. Now I'm going to change this graph in a very subtle way, so I want you to pay very close attention and see if you can spot it. All right, do you see it? I only changed one thing, which is the x-axis label. Instead of thinking about values of a covariate, like a school or a person, we can think of this x-axis to represent the items on an assessment, for example, a 10-item math test. And I can apply the same logic, right? Maybe my treatment improves the performance on those 10 items equally, or maybe I get the same average treatment effect that's just driven by a few items that saw very large impacts and some other items that saw no impacts. And if I further told you that, say, items 4 and 8 were multiple choice and the rest of the items were open response, well, maybe that's telling me again something about how this treatment is working, what's really going on, thinking about maybe mechanisms we might be able to test, falsifiable hypotheses that might be of scientific interest, for example. I think it's instructive with that picture in mind to ask, like, what might cause this? And again, I'm coming mostly from education, but I'll try to broaden it a little bit in some of these examples. I think one of the clearest causes, particularly prevalent in education, would be what we would call the alignment between the intervention and the outcome measure. Let's say I'm a math researcher, I develop a great intervention for teaching fractions, and you know, it works really well. But then if all I have to measure that is some state test given at the end of the year that consists of maybe 50 items, only 5 of which really capture fractions content, it seems plausible to me that those fractions items might see a treatment impact, but the rest might not, and also vice versa. Uh, Similar to what I just alluded to a moment ago, right? If instead of teaching math, I teach a test-taking strategy like process of elimination, well, that would process of elimination will help you, or rather, it will increase the probability that you get a multiple choice item correct. However, it won't do much, if anything, for say an open response item. So if we're seeing different types of effects on different types of items, that could reflect, say, teaching to the test or teaching a test-taking strategy rather than teaching mathematics proficiency. And last, to broaden it beyond education, a big issue people are worried about often in psychology and health is what psychometricians would call response shift, where the treatment makes the participants better able to intuit what the researcher wants to hear or makes them interpret the scale differently. A classic example would be social desirability bias. One study I was just talking about with a colleague, it was an intervention on like nutrition, and they had some questions about food knowledge. Do you know which foods are nutritious? But they also had questions on food preferences. How much do you like to eat cabbage and broccoli and so forth? And we might be worried about, like, if there's some social desirability, being part of these treatments may uh, have the effect of the participants learning, like, what the quote unquote right answer is, even on a survey of preferences. And if that varies across the items of an assessment, we could similarly see these types of effects. So that's just the very big conceptual picture of what I mean when I say an item level heterogeneous treatment effect and why it might matter. Now I'd like to make it more concrete by representing this mathematically. And to start, I'll just begin with a measurement model with no predictors. And I realize we have some psychometrics people in the crowd. I could tell from the chat comments, but in case you're not familiar, sort of one of the foundational models in psychometrics is called this 1PL or one parameter logistic model. And it's very simple, but it's also very intuitive. In essence, I say the log odds that person J answers item I correctly is a function of two things: your proficiency, your ability, your latent trait, theta J, this is whatever I'm measuring, and then how easy or endorsable an item is. The intuition here is, let's say, again, I'll use math. If I increase your math proficiency, I increase the log odds of a correct response. But also, if I give you an easier math item, I increase the log odds of a correct response. And this is very commonly used in, assessing the functioning of measures psychometrically. And we can extend this model very simply to allow for a treatment effect, right? By adding a predictor to the model, we can think of this as a multi-level model. So what I've done here is I've taken theta, which is my mathematics proficiency in this example, and I've turned it into a regression equation where I'm saying theta is a function of treatment status. So I have some control group mean for theta, beta 0, some treatment effect on theta, beta 1, and then some unexplained variation. And this is a simultaneous estimation of a measurement model at the top here and a regression model. So if you're familiar with item response theory or structural equation modeling or even multi-level models, that's essentially all we're doing here. But what I want to point out is that beta 1 is just a single number in this model, right? I am asserting or I am assuming by fitting this model that treatment is impacting all items equally because whatever beta 1 is, that will be equal across all of the items. So to relax this assumption, I can make the equation look slightly more complicated, but it's really a very simple change, which is that I'm adding this one term, zeta I Tj. This is giving me the item's specific sensitivity to the treatment. And what's really nice about this from an interpretive perspective, I think, is that we still get beta 1. I say, here's my treatment effect on the average item of the assessment. But item I may be above that average, it may be below that average, and then I can parameterize how variable this sigma zeta here, how much did those item-specific treatment effects vary around the average. And importantly, like that may be correlated with the item's easiness parameter. Maybe my treatment is really good at teaching easy content, but not hard content, or vice versa. So we can immediately start to explore how these treatment effects may vary at the individual item level. And while I will maintain focus on this very simple example here today of just like, a single treatment, or rather two groups and no covariates, I want to point out that it's really easy to extend this framework. Like if we have additional levels of clustering, or we want covariates, or we want interaction effects, or we want longitudinal models, it's very straightforward to take this framework and extend it. But I'm going to maintain focus just for clarity on the simple RCT case. If you prefer directed acyclic graphs, which I often argue with my co-author Ben about because he does not prefer them, but I sometimes find them helpful. Essentially, what we're saying is we're observing your item responses to this test, and your latent propensity to respond in a given way is a function of, again, your ability, theta, the item's easiness, B, and then also this item-specific treatment sensitivity interacted with treatment status. So again, this is allowing me to get a unique treatment effect for every item in the outcome measure. And just to tie it all together to bring us back to the Gelman visualization, what do these really mean concretely? We can think of beta 1 as being that horizontal pink line, right? That's the average effect across items. And if the treatment effect is above that pink line, it's going to get a positive zeta. If it's below, it's going to get negative. And that sigma zeta is giving me the standard deviation of that distribution around the pink line. Now, a psychometrician might say this sounds a lot like differential item functioning, or diff. And that is correct, right? We're saying above and beyond an improvement to your proficiency theta, item I gets this extra bump in either direction. And diff is often used to test for, like, say, bias by demographic groups. We want to ensure that a test is functioning similarly, say, for different ethnic groups, students of different ages, men versus women, and so forth. But here, I think it's less instructive to think about bias because the treatment is randomly assigned. I think it's more instructive to consider this as indicative of like a treatment heterogeneity, or if we want to think about the item itself as like instructional sensitivity. How sensitive is this item to an educational intervention, say? So what does this all look like in practice? Perhaps I've convinced you that this is theoretically interesting, perhaps not. But what I wanted to do with this study, and really the heart of it, is to see what does this look like in the real world? As I've mentioned before, to do this, I identify 75 public data sets from 48 randomized controlled trials that contain item level outcome data, some pre-intervention baseline measure that I can use, typically a lagged score or some similar metric, and then enough empirical information to verify how the items should be scored. For example, do some items need to be reverse coded? And I do share all of the data sets in the replication materials if you'd like to explore them yourself. These are public and a common format. I'll talk a little bit more about that at the end. And I've, in fact, since added about 20 data sets to this, so there's plenty to play with if you're interested. I also want to point out, again, I'm making a lot of simplifications across these data sets because these data sets are very, very different, but I want to illustrate sort of the logic of this model in a variety of real-world settings. I make several simplifications for comparability. For example, I'm comparing any treatment to any control to keep it binary. I'm only looking at initial treatment assignment, so looking at intention to treat effects. I'm assuming individual randomization, though, as I mentioned before, the model could be easily extended to, say, cluster randomized or block randomized or both. I'm only looking at the first follow-up for those studies that have multiple follow-ups. And importantly, I'm splitting apart multiple outcomes from the same study. For example, if I have a literacy intervention and I give you a vocabulary test, and then I give you a separate reading comprehension test, I'm considering those separately. And whatever this pretest variable is, I standardize it in the sample to mean 0, variance 1. And if I have item level data on the pretest, I created IRT-based scores to serve as a pretest. And there were a few data sets with polytomous or ordinal responses. You can think like a Likert scale, or rating something from 1 to 4 or 1 to 7. Just for illustration, I dichotomized those to keep everything exactly comparable, though there are extensions to this model that allow for continuous responses or ordered responses. Just to give a sense of some of these data sets, I'm not listing all 75 here, but these are just the first 12. I want to point out a few things. We have a range of geographic locations from the US and internationally. We also have a real range of outcomes. We have some things that are really common, like reading comprehension, but also things that are a little more niche, like financial literacy, uh, indicators of crime and violence, reading self-concept and so forth. So we have a really wide range of measures of populations, adults, children, different types of interventions. The ones marked with asterisks are outcomes where lower values are preferred. For example, you want your intervention to reduce depression, reduce crime and violence, reduce domestic violence, but you'd want your intervention to increase health literacy, financial literacy, and so forth. So I said there were 5 insights from this model. I'm now going to go through them again with the data this time. First, I want to apologize. The paper is in portrait mode, but the slides are in landscape mode. So I know the data set IDs get a little bit squished. So sorry for that, but we don't really need them. So insight 1 is we get item-specific treatment effects. And what I'm showing here is the y-axis is the dataset ID from our 75 datasets. The x-axis is the item-specific treatment effect. And the blue or red, the big circle is beta 1. That's our average treatment effect across all items. And then the little circles are the item-specific effects. And immediately I can see many of these studies are showing gigantic ranges of item-specific effects. They're color-coded by whether using a likelihood ratio test that variation in item-specific effects is significant. I can see that the majority is, and even just descriptively, I mean, look at this top study. I'm seeing a few items that have point estimates that are negative for the treatment effect. Where I look at this study down here, I have one item with a treatment effect of 3 standard deviations, which is, pulling up that average. Maybe I probably want to investigate what that item is to understand how sensitive my results are to it. So just purely descriptively, we're seeing very wide ranges that would be completely masked if all I had was that total test score. And as we talk about in the paper, it's easy to specify hypotheses and test them about what might drive this. I could say, again, are these effects larger on multiple choice items versus open response items, easy items versus hard items, right? We can think about how to parameterize and test all of those hypotheses. Insight number 2 is about the standard errors. What I'm showing in this figure here is on the x-axis is my estimate of the standard deviation of item-specific treatment effects, sigma zeta. And on the y-axis is the inflation of my standard error of the average treatment effect. So if it's 2, that means the standard error is double what it is when I assume a constant effect model. Why is this happening? I think it's sort of intuitive once you think through the logic of it. If in the population of, say, potential math items, all my treatment effects are constant, my treatment improves math performance by 0.5 on every math item, 5th grade math item, say. It doesn't matter which 10 or 20 or 50 items I choose for the math test, because if I choose item set A, item set B, item set C, I'm going to get the same estimate every single time. There's no sampling variability based on the items. But if in the population the item-specific effects do vary, well, if I draw item set A for study 1 and item set B for study 2, well, maybe I get lucky one time and I happen to draw some items that are particularly sensitive to treatment, or I get unlucky and I happen to draw some items that are particularly less sensitive to treatment. In other words, the items are a source of sampling variability in terms of our treatment effect. And this model essentially gives us inference for what is my standard error for the treatment effect on the population of items, not just the specific items on my realized test. It turns out we can quantify this very simply, which is to say the standard error under my model that allows for heterogeneous treatment effects is a function of the variance under the random intercepts model that assumes a constant effect plus the variance of item-specific effects over the number of items. So I can very clearly see that even if I have an infinite sample size of people, if I have a lot of item-specific variation, I could still get treatment effects that show sampling variability based on which items I select for a given administration of the test. Insight number 3 is the prediction interval, but I can also use this to illustrate insight number 2. So here again, I'm showing all 75 studies, slightly squished vertically. The red is the 95% confidence interval from the model that assumes a constant effect. The blue is the 95% CI that from a model that allows for the item level varying effects, so we can see how that becomes inflated, sometimes substantially. And then the black line is the prediction interval. This is saying if I drew a new item from the same population of items, where might that item-specific treatment effect fall? And just to illustrate why this might matter, take a look at study number 3, which is the second from the bottom here. This is a study of depression, and the intervention is a SSRI drug randomized trial. So if we just fit the standard model, which is my red 95% confidence interval, I see, hey, depression, or the drug reduced depression, it's statistically significant, it's negative, that's great. I allow for item level heterogeneity. Yeah, my standard error gets a little bigger, but I'm still confident that it's below 0. But if I look at that black line, the prediction interval, I'm seeing there could be some items that are positively impacted by treatment, or in this case, hurt because we want depression to go down. This reflects side effects of medication, right? SSRIs, and I'm not a medical doctor, but from what I understand, they help your mood, but they don't help, and in fact can sometimes hurt, say, your appetite, which is a symptom of depression. So we can see how this could be useful in, say, medical fields to understand, the probabilities of seeing negative side effects of a drug independent of its average effect across a set of symptoms on, say, a depression questionnaire. Insight number 4, disentangling interaction effects. This one is the most complex. In fact, I have an entire paper dedicated to just this single one. So if you want to read 9,000 words about that, I'm happy to share that with you. However, there's a figure in that paper and in the present paper that I've reproduced here that I'm convinced that if you can understand this figure, and I believe everyone in the room today can, you don't need to even read the paper because the intuition is all right here. So what am I showing? I'm looking at my test score on the y-axis, the expected value of my test score, and this is a 3-item test, so you can get 0 to 3. I'm showing on the x-axis some covariate. It could be anything, but for the sake of conversation, let's call it the pretest score. And then I'm showing the conditional expectation functions for the treatment group, which is the dashed blue line, and the control group, which is the solid red line. And if I show this figure in the bottom left to anyone in a regression class and ask them to interpret it, they would say there's a treatment by covariate interaction. X is interacting with treatment. If I look at low values of X, I see the treatment helped. If I look at values of X in the middle, treatment didn't do anything. And if I look at high values of X, treatment hurt. And the same is true on the right-hand side. I look at low values of X, treatment helps. In X in the middle, treatment does nothing. X high, treatment hurts. And there's nothing I can do just looking at that bottom row to distinguish these two figures, right? They look the same. And you might say, well, they should look the same, right? Like they are the same. What's the problem? Well, let's look at the item level, which is the top row. I'm now showing the probability of a correct response on each of the 3 items of the test. Now, if there is a true treatment by item or treatment by covariate X interaction, every item will be a microcosm of the overall test. And what I see here is at X equals -2, all three items are helped by the treatment. At X equals 0, all three items are unaffected by treatment. At X equals 2, all three items are hurt by treatment. And when I sum those up to get the total test score, I get my interaction pattern that I'm familiar with. No problem. But now let's look at the top right. Notice something is quite different here. If I look at X equals -2, one item is helped, one item is unchanged, one item is hurt. If I look at X equals 0, one item is helped, one item is unchanged, one item is hurt. If I look at X equals 2, you can say it with me, right? One item is helped, one item is unchanged, one item is hurt. And because these are curves and not lines, essentially I'm stretching out those blue curves, and that gives me what looks like an interaction effect between treatment and X, when in fact, all that's happening is that the easy item over here, which I'll circle, the easy item is helped, the middle item is unchanged, and the most difficult item is hurt. And those are two very different mechanisms of treatment impact. It's very different to say treatment helps low achievers than treatment helps easy content, right? And those are two very conceptually different things that if we're not careful and we're just looking at overall scores, can become confounded. And I have some more mathematical detail for this in the paper. And in fact, my motivation for writing the paper I'm presenting today was this slide here to say, okay, again, theoretical problem, how prevalent is it in the real world? And so what I'm showing here, and there's a lot happening in this graph, so I'll break it down, is I'm showing on the x-axis how much those item curves are being stretched or squished. So for example, if I go back here and I see those blue curves are being stretched out, that's taking me on this side of the graph. And what that does is it's lowering that slope of the overall line, which is creating a negative interaction effect. And that's what I'm seeing in these studies over here. These are studies where those item curves are stretched out, and I can see that that decreases the estimated interaction between treatment and the covariate. If I go this way, I can imagine I'm pushing those blue curves together. And what that does is it would steepen the line, or it would make my interaction effects bigger. And that's what I'm seeing on this side of the graph. Now, a few things to notice here. For a lot of studies in the middle, there's not a big difference. So we're safe, right? But the point is, if I'm just looking at the sum score or some factor score, I simply don't know how big a problem this might be unless I have the item level data. In some cases, the differences in interaction effects, and these are standardized, are quite large, right? We're seeing, in a world where the average intervention effect for an educational study might be 0.1, a difference in an interaction of 0.1 standard deviations, a difference in an interaction term of, say, like 0.6 or 0.7 standard deviations can be really troubling from an interpretive standpoint. Okay, last, and I normally would say not least, but this probably is least because this actually isn't unique to this model about item level heterogeneous treatment effects. This is true of all latent variable models. This model and all latent variable models disattenuate standardized effect sizes for measurement error. Now, you may have learned in a regression class that measurement error in the predictor variable attenuates relationships, but measurement error in the outcome variable just reduces power, but it doesn't cause bias. And that's true unless you're looking at an effect size. Why? What is an effect size? It's the mean of the treatment group minus the mean of the control group, which would be unaffected by measurement error, over the standard deviation. But the standard deviation is affected by measurement error because the standard deviation of an outcome variable, or rather the variance of an outcome variable, is equal to its true variance plus any measurement error. So when I'm creating an effect size, which is critical for meta-analysis, for policy, right, for comparing studies in different contexts. If there's measurement error, I'm dividing by a number that's too big, and therefore my effect size is driven towards 0. And that's what I'm showing on the figure here. The x-axis is showing my effect size from the latent variable model, and then the y-axis is showing how much smaller in absolute terms the effect size is on just a standard model that does not correct for measurement error. Again, these are big differences in a world where the average effect is probably zero point 0.1 standard deviations, we're seeing a lot of studies that are being biased towards zero by zero point 0.1 standard deviations or more. All right. To summarize and conclude, and I see we're perfect on time here. What do we gain from this modeling approach? Item level heterogeneous treatment effects. I opened by saying our guiding question was we almost always collect this item level data in RCTs in education. How can we leverage it more effectively? I've argued we get 5 insights from this modeling approach. Number 1, we can test specific hypotheses about item specific effects. 2, we get more realistic standard errors that account for the selection of items onto a test. 3, we get prediction intervals for out of sample items, which helps us understand how generalizable and consistent our intervention effects are. 4, we can correct and resolve those strange biases and treatment by covariate interactions I just referred to. And then last, we get standardized effect sizes that are corrected for outcome measurement error. So I think this can be really compelling. These are easy to apply, and they give us a lot of new insights into intervention data that we've already collected. And that's it. I'll just conclude again by saying you can get the paper at the QR code. I have my email down below. All of these data sets and more are now publicly available on the item response warehouse. You can just look up my name, Gilbert_meta, and you'll see them. I think I have 95 there now. These also have additional time points, covariates, some cool stuff. Also, to any of those of you who are maybe attending the National Council on Measurement and Education Conference or the American AERA, American Education Research Association Conference in April, I'll be doing a tutorial in R on how to actually fit this model and extend it and more of the interpretation as a pre-conference workshop on April 23rd. So if any of you are interested, I would be happy to see you there. So thank you again for your time. Happy to take any clarifying or substantive questions in our remaining 20 minutes.
Awesome. Thank you so much, Josh. If you have questions, feel free to either put them in the chat and I'll read them out loud or just unmute and ask.
And I am sorry about that Zoom pop-up thing. I had some software update. I couldn't get it to go away, so apologies.
I have a question if nobody else does. First of all, thanks so much for the talk. I really appreciate it. So my question is about kind of an artifact of these multi-level models. So let's say that you have, let's suppose that a whole bunch of treatment effects are 0, and then you have a few items where there's a treatment effect. Because the multi-level model is going to kind of shrink towards the average, isn't that going to pull up a lot of those effects that are 0? And then you'll kind of see some spurious effects start popping up. Like basically you're shrinking to the wrong place if you have items that don't follow like or effects that don't follow like a traditional normal distribution.
Yes, so your intuition is correct. They will be shrunken to whatever the mean is. And in fact, I can share a paper with Peter Halpin, who's a psychometrician who was at NYU. He's now at UNC Chapel Hill, that really looks specifically at this problem, where you can essentially do some iterative algorithms and processes where you can downweight these outlying items and potentially correct for those circumstances. So if you really had a case where you had 90% of your items are showing 0 effects and if 10% are showing positive effects, like his method would help correct for that. I think though, if we look at the empirical data, and I'll go back to the slide here. 1 second. There we go. I mean, what we would expect to see there would be like a lot of items piling up near 0 and then like some outliers, but actually like the assumption of normality looks pretty reasonable in a lot of these data sets. I think it's like there are counterexamples, and I think like this study right here would be one where you have like most of them near 0, and then you have this one sort of crazy one up by 1 or something like this. But the point is like that's a testable hypothesis, right? We can look at that model. We can relax that assumption. We could test it by excluding certain items. We could use Peter Halpin's method to downweight items that show aberrant behavior. But I think your general point is correct and well taken.
Thanks so much. I really appreciate that. I'll look into some of Peter helping stuff.
Yeah, and I'll put a link to it in the chat, and happy to follow up on email too.
I'm going to let Pac.
Should I go? So I have two quick questions. One is, does your program and approach generalize to a 2PL model if you have slopes? And the other one is, could you comment on what you think the implications are for, say, mental health studies where we don't sample items, we have fixed item sets, and the item sets, say for depression, are explicitly designed to span the clinical range of symptoms that seem to go. So, but it seems like there are different implications.
Yeah,
So could you comment on those, please?
Absolutely. So I'll take those in order. So the 2PL, yes, you can do 2PL versions of this model. I include the code at the end of the paper and a little appendix on how to do that. It creates some interpretation, like it's more difficult to interpret, but it can be done. And when I fit the models to all these data sets, we see that most of the results are very concordant. There don't seem to be, a lot of differences. And you could do 3PL, you could do graded response model, right? There's plenty of extensions in the IRT space. With respect to the mental health stuff, so I'm not, a mental health expert. I'm education where a lot of these sort of item sampling ideas are more natural. I mean, I think even in like depression, I mean, there are many depression scales, like even in this survey, like there's the CESD, there's the Hamilton scale, and even like the Hamilton scale, which has 17 items, like yes, that's used very consistently across many studies. But like, I don't know, maybe this is more a philosophical question. Like, could you actually enumerate all potential symptoms of depression? Or like, I could imagine adding more symptoms to the Hamilton scale that would potentially capture sort of different experiences of depression, like how do we think about appetite? Could I have more questions about appetite, fewer questions about appetite and so forth? But the point, again, is well taken. And in that case, if you really are convinced you're in a case where the pool of items is fixed, like maybe you have a pilot's licensure exam and it's the same items every year. I don't know if that's true or not. Well, then the standard error inflation is not really an issue because you're just saying, well, I only care about an inference to these specific items or to these specific symptoms, in which case you don't have to worry about it. But nevertheless, it could still be instructive to say in depression, like, okay, yes, this is the total list of symptoms of depression, these 17 symptoms. These 2 symptoms seem to be hurt by treatment X versus these 15 symptoms that seem to be benefited by treatment X. So it certainly will require some judgment on the context of the particular case, and that will certainly vary in health versus education, say.
Yeah, so just a quick follow-up comment. I think it would be helpful for the construct validity of the intervention. People do mediation studies to try to show that the intervention is doing what they think it's going to be. And I think you could see this as your method is another way to check for of whether the mechanism of the intervention is working. So I think it's very interesting. Thank you.
Yeah, and just to respond briefly to that, I totally agree. We talk in the paper about that specifically. And I alluded to this before, like if you have a fractions intervention, but you test it with a broad math test, like you would expect to see the fractions items move, but not the geometry items probably. So it can be a really great way to to use one of the words I use somewhere in one of the titles of these papers, to pinpoint the impacts of these interventions, to test scientific theories, look at mechanisms of mediation. So absolutely agree. Jennifer, I believe you had a question.
Yeah, I did. Thank you. Great talk. Super interesting. Peter used to be actually in our group, so we know
very nice.
Peter. But I'm trying to think of the best way to frame this. So people get concerned about, people might be concerned that and I apologize because I had to leave for like 5 minutes during your talk, so you might have covered this when I was gone. So apologies if I'm asking something you already said, but are you concerned about multiple comparisons, basically, right? If you're testing so many things, or do you think that if it's in, like, for instance, if you embed it in a multi-level model framework, we're not so concerned about that with the Bayesian of it all? But what's your thought?
Yeah, I would say a few things. One, I'm personally and like less interested in testing the statistical significance of every single item-specific effect, for which I think multiple comparisons could be an issue. However, there's a paper by Adam Sales and some colleagues that looks at this, and because like in that figure I showed, those were the empirical Bayes estimates of the effects. I think when he tested it through simulation, it was like the false positive rate's like 0.07. Because these are shrunken, like, yeah, it's a little bit inflated, but it's really not too bad. So I think the multi-level structure and the empirical Bayes portion of it can really help alleviate that concern. But I view this as more like, well, I'm just like getting that parameter of the standard deviation of effects. Like that might be what I'm actually interested in, rather than saying, oh, is item 7, is that effect statistically different from 0? But yeah, I think it's an important point, and one that I think this modeling approach, by using random effects rather than say fixed effects, I think it would be a much greater issue if like if I interact treatment with every item indicator, well, now I have 12,000 comparisons among my 50 items.
Yeah. I mean, because even though you're just focusing on the standard deviation, and the researcher is going to take the next step, right?
Well, I think that's the argument for the empirical Bayes rather than say a fixed effects approach, which I describe in the paper. Yeah, absolutely.
Anyway, really, really interesting work. Thank you.
Thank you very much. Appreciate it. Yeah, Chuck, go ahead.
Super clear, interesting. Some of the examples that you mentioned of sort of like how items are different, like method differences, and also sort of like subsets of a larger factor. I was curious if you thought about like specifying measurement models in a more specific way to sort of try to capture that, as opposed to after the fact trying to figure out what items have in common.
Yeah, I guess there's sort of two ways to approach that question. I think one is in terms of dimensionality, which is like, hey, maybe it's not that this item cluster is being affected differently than this item cluster. It's that, no, actually fractions in geometry are separate dimensions. We should be fitting multidimensional models. I think that is certainly one approach, and you could certainly take a confirmatory approach to this and say, hey, for example, I have a state math test. Every item is aligned with some standard. I could use those a priori standards to test some hypothesis. You could also go in the other way, which I've described here, of saying, hey, what's going on with this cluster of items? But I think things like item covariates, like those could be more objective, like say multiple choice versus open response. That might not map onto any real dimensionality concern. It's certainly not something that the researcher would, they can't change that after the test is done, right? Those are just objective item features. So I think there's a lot of opportunities here for both the exploratory work, which is more what I've shown here with these super broad application of 75 data sets. And as I describe in a few instances in the paper, some more confirmatory work. I think one of the best examples, and this relates to a prior question, was there was a literacy intervention, and they had a reading test with 3 passages that had a lot of shared vocabulary with the intervention, some shared vocabulary, and no shared vocabulary. And then you specify this model allowing for differential effects by passage, and lo and behold, the one with all the shared content and vocabulary showed the largest effects. The one with the smallest, with no shared vocabulary, didn't show any effects. So yeah, I think there's room for a lot of interplay with multidimensionality, with item covariates, with modality effects, exploratory and confirmatory. So I think I would agree with that instinct. I'm just putting that other paper in the chat here, which is sort of, I was talking with Peter Halpin about this, who we met at a conference last year. And so I view it as we're climbing the mountain from different sides. Like we're sort of looking at the same thing, but he has some different concerns. So I definitely recommend that for those who are interested.